So welcome to my presentation. So what we're going to talk about today is actually a research that, the main point about it is to show how to start from scratch, and then get to the point where you have vulnerability. And if there's something I really emphasize on taking from this presentation is the actual process of doing the research. So our agenda for today, first I'll briefly cover sandbox concepts, what is sandbox, usages, and why we need that. Then I'll go to some more specific Apple use cases, but still I'll talk about high-level things. Then I'll go through the entire path that got me to find this iOS vulnerability. And I'll also talk about a technique I used to, not to debug the kernel, but to make sure it's easier to trace that. And finally, I'll show some lazy thing I did to debug Apple processes. But before we start with the presentation, 30 seconds about myself. My name is Donenfeld. I've been a security researcher for the last couple of years. I focused mainly on mobile platforms, but I also have a little bit of experience with PC. My research is mainly vulnerability assessment and exploitation. Right now I work at Zimperium as an iOS researcher, and I also like to present my work in conferences. And I also live now in Europe. I moved from Israel to Amsterdam. So, sandbox. So operating system wants to protect sensitive attack surfaces, and it does that using sandboxing. That's something that the tendency to actually use sandbox to make the attack surface smaller is something that we've seen in iOS. Everyone does that, but Apple started doing that in the last 5 years more than ever, because Apple realized that instead of trying to fix certain bugs, it's just much better. It's much more practical to actually just close attack surfaces. We also see, we also saw that example in Windows, in Win32K, but Apple have been doing that for a lot of different mechanisms. Now, putting aside knowing the attack surface, sandbox is also pretty useful if you want to prevent apps from accessing specific information. For instance, our flashlight application is not supposed to be able to read our fingerprints. And CoreAuthD, for instance, which is responsible for some authentication and security things on the device, is not supposed to be able to access our calendar or our camera. So that's the known use case for sandbox. But as we can see, Apple actually introduced new sandbox rules because of vulnerabilities. A famous case was in 2015 when Mark Dode, I think that was the guy, he found an attack from AirDrop, I think it was a directory traversal, which just got you root access on the device because sharing D, which is the daemon AirDrop uses, was running, if I remember correctly, as root without sandbox. So Apple just put it into a sandbox, and now even if you have an AirDrop vulnerability, you'll still need another one to make sure you can elevate your privileges. And we also saw that recently, for those of you who used to jailbreak your phones 7, 8 years ago, all of the symlinks restrictions that now we have on AFC, that's why we don't see a lot of USB vulnerabilities like before. And if some of you remember my research from last year, I presented the fully working kernel exploits in 99% success rate, working pretty much instantly, but still it needed the sandbox escape. So even if you have a kernel exploit, if you have something that prevents you from accessing this certain attack surface, then you still have a lot of work to do. So actually sandbox, in my opinion, is much better than closing specific bugs. Or at least cost-effective wise, it's much, as an attacker, I would like to have bugs fixed and not attack surfaces being closed. But sometimes an app does need some specific permissions, elevated permissions, like sometimes, I mean, Instagram wants to be able to use your camera. So Apple doesn't want to give it direct access to the camera driver, but it still wants Instagram to be able to use the camera. So technically speaking, if an app wants to utilize the camera, not request an RPC to use the camera, but literally ask the device to use the camera, it will just ask, I mean, okay, a different example here, video decoding. If you want to encode a video, you have to talk with the video encoding driver if you want to do it in a hardware accelerated way. And that's how an app would normally do that. But on iOS, we have media server, which is a broker in that case, because if I'm an app, if I'm a video app, I'm not going to talk with AV video encoder, but rather I'll ask the media server to do that encoding for me, and then media server will reply back with the encoded video. Now, what media server does here is making sure I'm not trying to pawn the kernel and make sure that I do what Apple wants me to do. So even if I somehow have a vulnerability in AV video encoder, like Ziva, I'm still not good. I'm still not good to go from an unprivileged app, because only media server can communicate with AV video encoder. So, with that said, like every good presentation in iOS vulnerabilities, iOS surfaces. So I'm not going to talk about iOS surface too much here because, because it's not relevant to it's not entirely relevant to the presentation. So in a single sentence, iOS surface is an object in iOS. So if I'm process A and I want to send a lot of information to process B, instead of sending it 5 gigabytes, I can just map it in process B. And all process B has to know is a certain ID. So it makes everything much more faster. And it's mainly used for transferring frame buffer information and graphic stuff. So iOS surface can not only map information, but it also has a certain set of properties. Literally a dictionary, key value based properties. But if I want to create an iOS surface object and I want to put some properties, then the kernel does verify that I'm not trying to put some weird values in them. So 1 year ago, I found a vulnerability in iOS surface, which actually I never saw talk about it. So there is one of the properties that we have in iOS surface is something called a plane. It has a size, a base, and it has a lot of them. So there was a problem here. That's the planes. I'm controlling plane size and plane base. And there are a lot of different planes. So here it takes the plane base I'm giving it. It takes the plane size. It combines them together. And then it checks if the last plane base we had overlaps with the new one. And what I didn't think about here, the guys at Cupertino, is that this is a sign. If I'm putting a negative value, it will just treat it like an unsigned int. And this way I can make a buffer overflow here. So what it lets me do is putting a very big plane size, because I can put a negative plane base. And then I can override. Then I can go and, put a big size here, which is something Apple obviously doesn't want us to have. So, unfortunately, from an attacker's perspective, even though that looks like a powerful vulnerability, iOS surface only saves the planes as a value, as a property. So even if we have a big plane size number here, it's still not good enough to actually pawn something directly from the iOS surface kernel driver. We have to get something else to use that property and make sure that, for example, user mode daemon or another kernel driver uses that value because other processes and kernel and drivers assume that these properties are sanitized. So basically, what we want to know is what uses iOS surface, and obviously we want to go straight to the kernel. So instead of looking for user mode processes, I will start looking for kernel drivers that use iOS surface. So the way we do that is iOS surface is an object which we create using the iOS surface root user client. So if I'm a if I'm a process, I'm just creating a handle to this specific interface exposed by the iOS surface kernel driver. If you want to obtain a handle to an iOS surface object, like I said before, each iOS surface object has an ID. So drivers do that we're using the iOS surface root service. It's a kernel service, and as a user mode process, we cannot use that, but other drivers can. Now, the way drivers use other services in the system is literally by their name. So iOS surface root registers itself as IO core surface root, which means that if a driver uses iOS surface, this string will be in the driver. So in the most narrowed and simplest way, I was just starting to look for the string IO core surface root in the kernel cache, which yielded a list of kernel drivers that uses iOS surface. Now, like I said before, most of these are, not most, but like the camera interface is closed from a sandbox. We use media server to communicate with that driver. Some of them are not accessible from the sandbox, some aren't. But that's the list of drivers that actually utilize iOS surface. So, our vulnerability was about the property plane in the iOS surface object. And because most, if not, I think all of the drivers we have here are actually closed source. So again, going the most dumbest approach, I was just looking for the string plane in all of these drivers. And then a debug string appeared, and a very interesting debug string actually. PIO surface dest get plane blah 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 blah, and we see that they use planes here and iOS surface objects. Again, I don't really from the first view, it doesn't really mean a lot, but it's a good direction because the other ones didn't have anything to do with planes, at least in terms of strings. So going to the place where I had that string. I saw the following code. I hope it's readable. So, I assumed, okay, so in the drivers in X and U, they have vtables. So if I want to check whether an object uses calls a specific function, that's a vtable offset, and that's where it calls the function. So what I assumed because of that string is that x8 here is an iOS surface object. And when I took offset 110 in the iOS surface vtable, I saw that this was indeed the get plane size. And the actual use, the parameters that this function expects is just a single one, which is the plane ID. So x0 is the iOS surface itself because it's a virtual call, and w1 is the plane ID. Now again, this is just an assumption, but it's a very good one, in my opinion, because we saw like actual debug strings, and because the probability that this offset will match the actual string is not so high. So if it does match, it's a good sign. Now, if you guys remember, the vulnerability was a controllable plane size, and we see that we have a memset with the plane size with 80s, which we don't know yet what the 80s are. And to be honest, I still don't know what the 80s are till today. And we override something, I'm not sure what yet. But this looks like a very good start because we can call memset in the kernel with an arbitrary length. So yeah, so like I said, we get the plane size, it puts it in x23. x23 is the length parameter, which is being called to memset. I removed the assembly code above it, but it was just a duplication of this one. So this memset calls the same function, but put here 0. So it was 0 here, but it's the same thing. So, okay, recapping here, we have an override with 80s with an arbitrary length. Sounds interesting. But to actually do something with that, we have to actually understand what Apple D5500 is. And I'm going to say D5500 because this is too long to be said so many times in a presentation. So, D5500 is a video decoding driver, a hardware accelerated video decoding, which is unfortunately not accessible from the sandbox, but we'll see an interesting approach soon. And to communicate with that driver, we have to use, like I said before, media server D. So if I'm an app and I want to have a decoded video, I'm sending a decode my video please request to media server D, which checks that I'm not trying to mess with anything, because this driver is extremely, I mean, it's like a glass. I mean, I don't know, it was like, I mean, if you have actual access to this driver, at least if you had, it wasn't that complicated to get it to crash. And if you guys ever took a look at media server D, it's the same thing. Some of the legitimate APIs crash media server D. So media server was making sure we're not trying to do anything bad here. Then it forwarded the request to D5500. D5500 sent the decoded video back to media server D, which sent it back to us. So a very unfortunate thing happened while I was doing this research. Apple silently closed this vulnerability. That was the only two assembly letters. That was everything they needed to actually fix the vulnerability. And I'm not sure who found that or who reported that, but I never saw any credits on their security advisory. But I was still very curious about what I saw, because the mem set with 80s is something I don't understand. And surfaces are always fun when it comes to iOS. So I kept with with my thoughts about D5500. So I wanted to know how we get to this function, because I was just looking up a string. So I wasn't exactly sure how I'm going to get execution here, because just in the middle of the driver, and the driver is not open sourced and not documented at all. In fact, if you Google that, the only things you see are crash dumps. We just mentioned that as a loaded extension. So looking up xrefs to this function, first of all, there were like billions of them. And again, no sources, so go figure out what it means. Some of them were actually virtual, so we don't really have an xref. You have to either write your own tools to help you with virtual calls, or just guess. And again, how can you actually make sure that this function is eventually reached? Because if you have so many functions, I mean, how can you know that? And I knew that this is going to happen a lot. Okay, I have a function, does it get reached? And for that, I have had an interesting approach. I took the YALO project, thanks for Luca Tedesco and Marco Grassi for that, by the way. And they have a remap page macro. They had, I mean, it's not, today it doesn't work anymore as far as I know, which was disabling KPP for a certain page. So what I did, I just disabled the KPP for a specific page. And then I overwrote 4 instructions on the address I was trying to trace. So ultimately, my goal was to give a specific kernel address in my project. And whenever this address was executed, I wanted to be notified about it. And I wanted to see all of the registers in that certain moment. So what I did, I called it YALO++. Let's say that I wanted to trace the execution context in address 118. I first called remap page on the entire page. Then I allocated the shellcode, which just pushed all of the registers to the stack, called kprintf, had some 4 stubs here, and then just returned back. Then, what I did, I overwrote the code here in 118, so that it will actually jump to my shellcode instead of executing that specific instruction. And the overwrite, like I said before, was with LDR x16, loading 8 bytes upfront, then calling the address, and then calling the jumping to that specific shellcode address. And then what I also did was overriding the 4 instructions I overwrote here, I put them here. So then the execution will seamlessly go back to where it was. I also changed the ret address here, but I didn't put it in the square. But there is also modifications to x30. So it goes back to, to the appropriate address and not to 11C. And this way, every time 118 was executed, I was notified about it. And I was actually surprised because it worked better than I expected. And it was extremely powerful at least for me, when I was working on kernel drivers, closed source ones at least. So around the place where I saw the string with the memset, I saw the same behavior again, same approach, some length. I'm not sure exactly what it did, but again, I can assume it might somehow be related to iOS surface. And again, this 80 with memsets on something, I'm not sure what it was. And okay, I understood at this point I can start reversing like a distant person the driver. And for that, because I had the kernel tracing technique. So I'm not going to go deeply in that, but basically you have to, there are some key rules when you start reversing a driver. First of all, you have to know where the vtables are and where they point to. And if you can automate that, that would be fantastic. You have to know the entry points to the driver. And in Linux, it's ioctls. In iOS, is new, it's external methods most of the times. And again, I highly recommend automating that. It is possible to do that manually, but it's really not fun. And a lot of people claimed to have, to release tools about it. I think Sigusa did actually release something about it, but I honestly didn't take a look yet. But IDA works well on that. And I think writing something that's on the way while you start reversing something is actually a very good approach. Okay, so like we said before, 80, the memset 80 had something to do with iOS surface in the driver. So let's examine the iOS surface usages in the driver. So like before, simple string search for iOS surface in the specific driver and allocate kernel memory, look up surface failed, which is perfect because that's where they look up the iOS surface objects. Now I put this code in, took a snippet in C because it was too long for if it would be in assembly. Now what I did here is I assumed v24 is an iOS surface object. So while all of that might be false, I did notice some very unique pattern for usage of iOS surface objects, and that is, like I said before, with iOS surface you can map memory from process A to process B, and the way Apple do that is using something called IO memory descriptor. So I saw that there was a function, a vtable function in iOS surface which created an IO memory descriptor object. Again, this was just a guess, but I saw that offset-wise, it was calling the same API that you would call when you actually use, in a proper use of iOS surface. So IO memory descriptor map, which returns us an object called IO memory map. It's not really relevant here, but the thing is, it does look like an iOS surface pattern. It's a lot of guessing, and you cannot be certain for 100%, but it does look like, in terms of the offsets, it looks like an iOS surface usage. And that's the thing. That's the interesting part here. Even if you're not sure about it, just guessing might be a good start. Now, okay, the offsets I saw here in this struct I called surface props somehow match the same offsets I saw in memset. Again, allegations, but it looked like the same thing. So then I just used the kernel tracing technique I showed you before, and I saw that this was indeed an iOS surface object, and that and that memset, I didn't get to the memset yet, but this was for sure an iOS surface object because I was just tracing the address of the vtable, and it matched the one that iOS surface had. So I knew that for sure that this is an iOS surface object here. Now, the thing is, obviously, because our vulnerability was with the plain size, we want to be able to supply our own iOS surface object. That's the thing. So for that, I had to reverse the actual call for media server because, like I said, it's not accessible from the sandbox, but because this API gets a lot of user mode objects, a lot of complicated ones, I assume maybe we can somehow affect if not the actual iOS surface object, maybe its properties. So I know that media server is the one that calls the 5500, mainly because it always crashes when you call it, when you use it. And when I searched up the string d5500, I actually didn't see it in media server. And the closest thing was something called video toolbox, which I saw first time when I started this research, because it had some video decoding related functions. So yeah, we have to reverse video toolbox. Now this is really painful because it's in something called daily child cache, which is so in iOS you don't actually have libraries. You have a big file called daily child cache, which is like I think more than gigabytes now. Now IDA 7 claimed to support it. I beg to differ. It's a very bad implementation. I'm not sure who's to blame, but even on IDA 7, it wasn't that good. But before that, they didn't even claim to support it. So I was actually working on an IDA Python script because if you put it in IDA Python, you just don't have branches for most of the functions. So I created an IDA Python script that made sure that we have those branches. And 2 days later, they released IDA 7. So I worked like at least a full day on that script, maybe even 2 days. And then I didn't even have to use it. But shit happens. So, no apparent usage of D5500 in video toolbox as well. So at this point, I was a little bit lost because like you cannot debug media server D or this extension while it runs on media server D. So I guessed maybe there's another framework involved. And I was just looking up the string D5500 in the entire daily child cache, which took like 2 days to load in IDA. And then I found that there was an interesting unknown framework called H264H8, which actually did a proper usage of the APIs to talk with the driver. So I did see that in a function called appld5500 decode frame internal, there was this API, which is the API Apple supplies if you want to use exposed interface of drivers. So every time you call that function, you actually send a request to a driver. So the actual exported function in H264H8 was this one, this long function name. But unfortunately, it didn't have any xrefs. And I mean, most of the code, I'm saying most because sometimes it does happen, but most of the code isn't written not to be used. So I thought it might be maybe in a vtable or something, and because IDA and daily child cache aren't good friends yet, maybe it just didn't parse it. So then I was like, okay, I'll just search the address in IDA and see if I find something interesting. And yeah, I found it in a vtable, in something that looks like a vtable, which also didn't have an xref. And then I started going with the same technique of, okay, if it doesn't have xref, it's just because IDA doesn't parse it. And then I just started searching for the address again. And I saw that there was a vtable and another vtable-like thing, which was contained in another vtable. So eventually, this one did have symbols, did have xref, sorry. And going up the stack trace, an object, a call, which is named blah 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 decoder create instance, was actually being called. And if you can see here, specific video formats were given to a function, which is not really. I mean, there were a lot of functions. I'm not going to go through each one of them, but I still want to show you the hierarchy. So the function H264H8 register, which calls this one, also didn't have xrefs, but it did appear as a string somewhere. So what I realized is that it actually uses dlopen and dlsim to call that, which I think is weird considering the use of daily child cache. So again, this is the flow I had to go. from the moment I send the request to media server till a driver was being used. So I'm sending an XPC request to media server. XPC is, by the way, some API, some IPC mechanism that Apple creates. Basically, you can send information easily in a dictionary or other nice object style. So you do that using an undocumented API called VT decompression session create, which is getting, I mean, you actually call that in your process, and as far as I remember, that's the actual same function which is being called in media server. And there's like a check. If you're a media server, then do something, otherwise just send stuff to media server. So this function calls development DLC, which calls H264 register, which calls this function, which creates an object with a vtable, which is another vtable, which is another function. So this wasn't fun at all to reverse, but we have to do that. So, I mean, the main problem was seriously IDA. Not even because, it's just xref with string search, but it was super slow. So this API, I mean, all the VT, the compression, blah, 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 wildcard things are actually documented in the sense that you know what the parameters they are expecting. And I figured out perhaps this is, I mean, that sounds like something that is related to iOS Surface because it's actually decoding frames. So maybe that's a thing that, that's the thing. I mean, none of the APIs actually talk about an iOS Surface ID being given to an API, but it must be there though somewhere. So this function, this function was calling this function within the H264 Edge 8 framework. And then, completely undocumented, I saw the following code. A while dictionary appears, and then you could supply, I just reversed the entire chain I showed you. And then I saw that if you supply the dictionary, the API can retrieve a dictionary. And if you supply this dictionary, it gets some parameters. This is completely undocumented, and it's accessible from the sandbox. And if there's a good, in my experience, if there is an iOS surface, there is a bug. So, at the moment I saw that, I was like, okay, finally something good is going here. And I obviously had no idea what offset X and offset Y were, or what last style was. I did know that canvas surface ID sounds like the actual surface ID we give to the driver. So yeah, like I said, it optionally receives an iOS surface ID. It also receives some offsets. And I wanted to check whether this was the surface we saw in the kernel. And using the iOS kernel tracing technique, I did, and it was indeed the specific iOS surface object we specified. This is another example how this was useful, because without having that, I cannot think on a way to actually make sure that this was our iOS surface object. So I understood that what I supplied here was going directly to the kernel, and it was accessible from the sandbox because media server D just used it and passed through the request to the driver. So our objective was to get to the memset, as I hope you remember. And at that point, we already had control on the iOS surface we supplied. So I just used the iOS kernel tracing technique on the memset area. Now, this is the memset, and this is tile offset X, tile offset Y are what we supplied in this dictionary. And if you see here, an interesting thing, tile offset Y and tile offset X are being given here. And these are all iOS surface properties we fully control, or at least in a very good, it depends on other properties sometimes, but in that case, I don't think there was any restriction, if I remember correctly. And this was given to plain offset 1 here, which is being used here as the length. Now, not only we control the length, we can also control the offset from where we start overriding. So this is much more powerful because, overriding a lot of things is one thing. Making sure where you actually start overriding is extremely powerful, because if you can actually utilize this memset and you can write this 80 on a specific length field of a different object. So, I mean, this is good enough to start working your way into a very powerful read-write primitive on the kernel. So, I mean, once you have the offset controlled as well, this is a completely different game. So, there was one problem though. I mean, and if I put the kernel tracing technique here, I saw that these were indeed my properties. But context, some unknown data, unknown. I mean, this expression was always preventing the code flow from going into the memset. Now again, there are 20-something functions dipped in the driver. I mean, how do you find out what this is? So because there's no source code, there are no extras because it's a struct offset. So how to find out what it is? So I looked at the assembly, and that was ultimately the check. They took something for offset 448, and then they took the 6 byte from it, and they ended it with x30. I had absolutely no idea what it was. And then I did the, again, most dumbest approach. I just dumped the entire driver's text section and started grabbing. So, nothing, no magics. It was just dumping the kernel and literally grabbing the offsets with str. And fortunately here, there was a good candidate. That was the only store into offset 448. So I went to this address. And if it's the only one, then we can safely assume that this was the object we were looking at. But here, we had x28. Now, I'm not sure how much pain you had from reversing drivers in iOS, but x28 is a function of the OS object. So every time you release a ref count on an object, they use the offset x28. x28, and x20 is retained. So you cannot grab x28 on a kernel driver. You have hundreds of matches. And at this point, I unfortunately had to start reversing like 15 functions. And again, you cannot have the compiler. You seriously have to go through the offsets and hope that eventually you find something useful. So again, I think this was really, I was a little bit miserable at that time, but again, I was, on the other hand, really curious to get to that memset. So, and eventually I got to that point, so I saw what they put in the x28. As I said here, we have x28 from which is being given to 448. So as I said, it was the 6 byte, and I saw that there was some calculation, which I'll translate it for you. That was the arithmetic that was done and being put in that specific thing. Now, again, it's the middle of nowhere. We have no idea what we're looking at. But again, 1B0 is a little bit less common. So I did the same approach. I just grabbed 1B0 with str, which yielded the following offset, which yielded the following interesting string. Blah, 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 blah. Age 264, FW, set PPS and SPS. No idea what it is yet. Now, there's something you didn't know about me. I never liked H264, and I never knew anything about H264, except that that's what I download when I want to see movies. And again, further looking on the check, I literally Googled I just looked around the function, and I saw another interesting string, AVC decoder parse header, unsupported NALU length size. So I Googled AVC NALU, and the first result was, welcome to H264. No, thank you. And at that point, I understood that having the standard might be useful. I would try to be honest, I would refrain from, I would try to do anything. Reading the standard is seriously the last thing you want to do, but it was very useful eventually, and you'll see soon why. So I'll summarize it for you. A video is actually a bunch of null units, hence NALU. So just a bunch of null units. So you can actually, everything you see in a video file is a null object. And I'm not sure if you can see anything from here. So I'll try to zoom because there are a few fields which are important. So there is a lot of things in null objects, and to be honest, I'm not really sure what they all mean because, I mean, people do a PhD on that, I guess. And but there are some header offsets in this specific object, which are very important here, are the forbidden 0-bit, which is, I have no idea why they put that, but that's a standard, so yeah, we have to comply. Null ref IDC, which I mean, it wasn't relevant to the research, and I didn't have to understand what it was. I mean, I assume it's a reference, but I cannot give a guarantee on that. But null unit type is something very interesting because this defines how we process the null object. So, I mean, we had a lot of things here, but after them, everything that happened was based on this null unit type. So again, each null object has a type, and I mean, now that we know that, and we know that we are talking about null objects in the kernel, how do we find where the kernel processes the specific object based on its type? So I got into that specific code, and I saw 0 null ref IDC with IDR, see, in this label, which is being called here. Now we see that there is a branch not 0, and I mean, if this is 0 and this is 5, this string is being printed. Now, going back to the manual, we did see that null ref IDC, and we did see unit type. So it might be, I mean, I was confident enough to assume that they might come after each other in the struct in the kernel. And as you can see, they just pop them from the object consecutively. I mean, in the same order. So, and I saw the word IDR, which is, I don't know what. So again, I just looked for the string IDR in the manual. And that's why sometimes manual are important, but really vicious. And I found out that number 5 in the null unit type is something called IDR. And as we saw here, as we saw here, there was a comparison to 5. So now we know that not only this is a null object, we actually know some very important offsets in that object. And at that point, it was much easier to go and see the actual processing of the object. And then what I saw, there are a lot of null types. I'm going to go through the important ones for this specific research, but there are billions of them. And I won't be surprised if there are other vulnerabilities there unless Apple revamped the entire driver. So the first one that we have to know about is something called SPS. So if we have a driver, if you have a video, so there are a bunch of properties for a short video sequence. So just like a few seconds, it depends. It can be a few seconds. It can actually be the entire movie, but just a bunch of properties for a specific duration. PPS, picture parameter set, is the same thing like SPS, but for pictures. So a bunch of pictures had PPS like properties like PPS, and there was also something called IDR, which is seriously like a BMP. It was a standalone image. So for those of you who are a little bit more familiar with video encoding, you have like a picture, and then you have only the modifications between each frame, and that's what is stored in the file. So IDR was a complete standalone image, so you couldn't go, it didn't need any other frame to be parsed, and other frames were based on the IDR they had before them. So for each SPS, so for each short video, video sequence, the IDR null was the first one. So this is how it looks in the video. You have the SPS object, the PPS object points to the SPS, and then we have an IDR object, and afterwards we have the frames. So this must always be the first one, and this must always point to SPS. By ID, by the way. They have a specific ID, and they just point to each other. going back to the research, we had the string set PPS and SPS, and then I figured maybe 1B0 is actually an SPS object or a PPS object. So what I did, I seriously sent a video to be decoded, and then I checked using the tracing technique if it was what 1B0 was. And it indeed looked like the SPS I was sending in the video. Now, a note about it, I started using FFmpeg because I was too lazy to, actually go and parse videos on my own. But then I found out that sometimes all these public tools are not enough. So it sounds harder than it actually is. There are a lot of actually good parsers in GitHub for H.264 videos. So I just took some, I just wrote my own tools to decode and to create and to parse videos. And I know it's a lot of infrastructure work sometimes, but eventually it's worth it. At least in my opinion, because this saved me a lot of time in, open 101 editor and start writing bits. So like I said, 1B0 was our SPS object, which was sufficient to understand the mysterious memset expression that we didn't have back then, if you remember. So if a property called chromoformat IDC is 0, we can get to the memset. So what I did, and by the way, this means, if this is 0, it means that the video is monochromatic, so only black and white. So it controls the, if I'm not mistaken, because again it's a standard, so it controls the colors for the video. So what I did, I was just using the tools I wrote. I created a video with chromoformat IDC 0, and I tried to decode it. So the way you do that with the API, you call the very long function name cm video format description create from H264 parameter sets. From now on, from H264 parameter sets, because I'm not going to say that every time. This initializes the session with with media server, and it receives PPS and SPS properties. The session the session needs the output from this function, the session creation API. And then we call VT, the compression session, the codes frame, and then nothing happens. Now, I'm not sure how it looks now, but I was, imagine you work like 2 weeks just to get to a specific instruction, and then you're like, okay, I'm finally getting there, and no, nothing happened. I was very, very frustrated at that moment. So I saw that we didn't even get to the point where the driver was being used, and then I reversed media server D, and I saw that media server checks if chromoformat IDC is not 0, and if it's 0, it denies the request. Now at this point, I'm like, after all the reverse engineering and the tools and everything, but then in a rainy day, no, in Israel it never rained, and I was still in Israel back then, so in a sunny day, yet depressing one, I read the H.264 format, which revealed the following. So each frame pointed to a PPS object. And every PPS object, by ID. It's imported by ID. And every PPS object pointed also by ID to an SPS object. And like I said, SPS object had the chromoformat IDC. Now this got me thinking, why do they need an ID for an SPS object if there is only one? Because if you look at FFmpeg, if you download a video from YouTube and you use FFmpeg to analyze it, there is always one SPS object. Also, when you parse a video, they never have more than one. And of course, I don't want to start writing my own video with bits. So I usually just downloaded the video and parsed it and maybe modified it. But then it got me thinking, maybe there is more than one SPS object. And then I read the following. Don't worry, there is a nice infographic later on. I hope you can see it. I cannot zoom because it's too wide. So, blah, 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 blah. It's most one sequence, each sequence parameter set, so each SPS is initially considered not active at the start of the operation of the decoding process. At most, one SPS is considered active at any given moment during the operation of the decoding process, and the activation of any particular SPS results in the deactivation of the previously active SPS, if any. Which means that standard-wise, I never saw any video utilizing that functionality, but the standard says so, so we have to comply. You could have theoretically a lot of SPS objects and a lot of PPS objects, and each PPS object could point to a different SPS object. So there was completely no serious relationship in terms of they can each SPS can only be pointed by a single PPS. I mean, you could just point to whatever you want. And in terms of design, this function was receiving only a single SPS and a single PPS object. And because these are it's video packets which are being sent asynchronously, this function couldn't get these ones. I mean, this function could only get the first SPS that was being used, because this could be sent later on after we already started the decoding, and this one was checking the Chroma format IDC field. So basically what I could do is, let's say that we send packets to this square, and this square decodes the video packets. So if I'm sending a frame, and this is currently active, and that's the current state of the compression of the state machine, this slice could point to PPS2, which points to PPS1, which deactivates, which points to SPS1, which deactivates SPS0. So again, I thought that a lot of there could be more than a single SPS object, and because this is only called once and only in the beginning, I had the following idea. I'll just create a normal session with media server, and I'll send it a nice, colorful video, and then I'll just send it an SPS packet with Chroma format IDC equals 0. So like, hey, I'm a colorful video, and all of a sudden a packet which changes the entire video to a monochromatic one. And if you think about it, it doesn't make any sense, but standard-wise, it's legal. So then I just created the PPS to point to this new SPS. And then I sent a slice which pointed to the SPS, which pointed to the PPS. And then finally, I got to the memset. After 2 weeks, I found it. I mean, it took me 2 weeks from the moment I saw the memset to get to this point, which is, I mean, more frustrating than it sounds, but it was seriously, it was very anticipated. So again, the code flow, I sent a normally looking video. Yeah, this is how videos look like if you open them in 101 editor. And then I created a new SPS object and a new PPS object which pointed to the SPS. And then a new IDR, because IDR must be the first slice that is used in the SPS, which pointed to the PPS, to the SPS, and so on. Finally crash, let's go to Apple. And now this was around Black Hat last year. And all of a sudden, the most modern operating system in the world, it's always the most operating system in the world, went out. And okay, cool. So I looked at the betas. I remember it was, I was sick in Vegas, and yeah, that's what you do when you're sick from the weather in Vegas. And suddenly it doesn't crash anymore. And you saw the way I was going through to get it crashing. And I mean, I was super disappointed that it didn't crash. And so I checked H260, the kernel driver, and I saw that there was no apparent change in the driver, which was good because the vulnerability was eventually in the kernel driver and not in the user mode components. But H264, I mean, the private framework which heads the Canvas Surface ID is changed. The Canvas Surface ID string no longer appears in the framework. And I know it sounds weird that I'm talking about strings in a framework, but seriously, I have no idea what it is to use either on these frameworks. So Apple realized that having this in a dictionary, in an undocumented dictionary, is a very hacky way to treat tile decoded videos, tile decoding videos from normal decoding. So they just created a new API for decoding and a new API for tile decoding. If I remember correctly, back then, tile decoding wasn't documented yet, but you could call the API. It was already there. Now, at that point, I just, if you have kernel read-write, then you can use debug server to actually debug stuff. I mean, you can launch debug server and connect to media server, but it doesn't work if you do it out of the box. And then I went to some old Wikipedia page which tells you that debug server needed the following entitlements. It also didn't work. And then I said, maybe I'll just give the same entitlements to media server. And then I'll try to launch debug server and attach it to media server. Then it worked. I could debug media server. And the main reason I wanted to debug media server is, first of all, I wanted to go to the API where it sent a request to the driver and change the values and see if the crash still happens. And second of all, I want to see what they actually did in the new API there. It was just faster debugging than using IDA back then. So, like I said, they understood that it was a hack, so they added a new bunch of VT tile decompression APIs. I used debug server and I changed the values, and it crashed again. So what I understood eventually is that there's just a new API, not a documented one, unfortunately. So here there is like a 64-bit integer which gets the offset X and offset Y that we saw in the dictionary. CV pixel buffer has inside it an iOS surface ID. So if you create a CV pixel buffer with an iOS surface object, so it will just use the same surface ID to the driver. So then you could instead of using the dictionary, you could just call this API and it would crash instantly. But again, it wasn't documented, so it did take me a while to find it out. So in terms of disclosure, I found it. I don't know. I mean, there was a gap between iOS betas till, it took me a while to get back to the research. And then I reported it. A month later, Apple confirmed it. And in the end of January, they deployed it to their devices. I know that it might be a little bit old comparing. I mean, we're in the end of August now. But I mean, there are some takeaways I really want you guys to take from this presentation. Sometimes, manuals, they suck. We don't like them. They are, I read quite a few in my life and it was never a fun thing to do. But sometimes they're super useful. Without the manual here, I would never think about creating a new SPS object. So, that's what got me eventually to trigger the vulnerability. Infrastructure work. The kernel tracing technique, without it, I would probably give up at some point because you have no idea how powerful, you probably have if you ever worked with drivers. It's just insane that you can debug or at least trace code execution in the device. So it was working even days or weeks on something like that if you can later on debug the kernel. And like always, iOS is a really good platform, but it still has a way to go. And usually, the vulnerability itself wasn't extremely complicated, but I think the path there was, I think it's sometimes more interesting than an actual exploit. If I compare it to to the presentation I did last year, this was much more complicated. So we have like 35 seconds for Q&A. So thank you. I hope you enjoyed the presentation. I know it wasn't easy.
Thank you very much, Adam, for a very interesting talk and also for being the speaker who comes closest to the timeline allocation. That deserves an applause.
I still managed.
Thank you.
Thank you very much.
Perfect timing as well because this breaks us for lunch. We have an hour for lunch and we will see you back here for lunch.
I'm available on Twitter and if you have any question, you can catch me later and I'll be happy to answer.
Yep. Any questions as well? You'll also be there at lunchtime.
Yeah,
so
of course.
Feel free to join us and join him. Thank you.
Thank you.